In the previous video, I introduced the continuous time version of the Ramsey model and set up the Lagrangian, which I've just rewritten here. So now let's go about optimizing this thing. So firstly, let's deal with the inequality constraint here. Remember this budget constraint we said held with inequality. So whenever we have an inequality constraint, we need to use the Kuhn-Tucker conditions. And if you remember, they are that the Lagrange multiplier, lambda, is going to be greater than or equal to 0. Our budget constraint itself is just going to be greater than or equal to 0, so that's just recovering the budget constraint. And the complementary slackness condition is that the Lagrange multiplier times the budget constraint is going to be exactly equal to 0. So lambda times the budget constraint. Equals 0. Now, if you remember back to our full budget constraint, remember we said this thing inside the square brackets held with inequality. There was a slightly longer expression involving the limit of C capital T times A capital T as capital T goes to infinity. We said that that held with equality. So this full expression, which remember we derived just by integrating the budget constraint, the flow budget constraint, which was just a linear first order differential equation, integrating that with respect to T, and we got this expression. So now clearly if we multiply both sides by lambda, on the left-hand side we just get our complementary slackness condition, and on the right-hand side we get this, which is equal to 0. Now this is our transversality condition. And our transversality condition, if you remember, says that the present value of your wealth as t goes to infinity must be equal to 0, or in other words, that your wealth cannot grow faster than the interest rate. And so this term here is equal to 0, and you'll actually see that lambda, when we come to derive the first order condition for consumption, you'll see that lambda is also going to be strictly positive. This limit as t goes to infinity of ct times at is also just going to be equal to 0. And so our budget constraint up here, which we said held with inequality here, actually this is always going to bind. This is always going to hold with equality. So the present value of our consumption is going to be equal to our financial wealth, A0, plus the present value of our labor income. So that's the budget constraint dealt with. Let's actually optimize our objective function by choosing CT. Now this is not like a normal optimization problem where you choose a variable to maximize a function, because now what you're choosing, C of t, is actually a function. Consumption is a function of time, and we're choosing that function to optimize this functional, this integral. So how do you choose a function? Well, you still take derivatives and set them equal to 0, but now you're taking derivatives with respect to a functional. That's called a functional derivative, and the way it works is like this. You consider a variation on the function, ct plus epsilon ht. Epsilon is just some scalar, and ht is just some arbitrary function defined from t equals 0 to t equals infinity, just like consumption. So if you want to think of this graphically, perhaps easier to think of finite bounds, so from 0 to t, consumption, our optimal consumption might look something like this. So this is c of t, and this ct plus epsilon ht might look like this. So this is C of t plus epsilon h of t. So here h of t is just something like this. This is just h of t. And to maximize this Lagrangian with respect to the function c of t, we're going to replace c of t everywhere in the Lagrangian with this variation. We're going to take the derivative of the Lagrangian with respect to epsilon. We're going to set that derivative equal to 0, and then evaluate the derivative when epsilon equals 0. So let's do that. Let me firstly just rewrite the Lagrangian. So I've just rewritten the Lagrangian everywhere, replacing ct with our variation, ct plus epsilon ht. Now I'm going to take the derivative of this Lagrangian with respect to epsilon, evaluate it when epsilon equals 0, and set the derivative equal to 0. And epsilon appears twice, appears here and here. And whenever you want to differentiate an integral of some function, so we're differentiating with respect to epsilon here, but epsilon is inside this integral. Whenever you want to do that, you can use Leibniz rule. And because the bounds of our integral don't depend on the thing we're differentiating with respect to, epsilon, we can just change the order of the integral and the derivative. So in other words, the derivative of an integral with respect to epsilon is the same as the integral of the derivative of some function with respect to epsilon. So this gives us an integral from 0 to infinity, e to the minus rho t, and take the derivative of u with respect to epsilon. So we get u prime of ct, and we're evaluating this, remember, when epsilon equals 0. So the plus epsilon ht, I can just forget about that. And then that is multiplied by ht, and then we close our integral. The second time epsilon appears, we need a minus lambda, and then again, just use Leibniz rule to take the derivative under the integral sign. And this whole thing should be equal to 0. Now these two integrals are both with respect to time and over the same bounds, so we can just combine them into one. So let me do that. And I've also just taken ht out as a common factor here. So this whole thing, this whole integral should be equal to 0. This is our first order condition. Now there's two ways this can happen. This can happen either by ht being equal to 0 everywhere, or it could be that this term in brackets is equal to 0 everywhere. This ht, sometimes called a test function, this is just some arbitrary function, so there's no reason why it should be 0 everywhere. So this implies that this term in brackets is indeed equal to 0 in order for this first order condition to hold. So this is our simplified first order condition. And you can also note that when t is equal to 0, this discount factor just becomes 1. And we get u prime of c0 equals lambda. So lambda is just equal to u prime c0. So if I go back to our transversality condition, remember this is what it looked like, we can now plug in lambda ct into this transversality condition and get back a perhaps more familiar form of the transversality condition. Our transversality condition becomes the limit as capital T goes to infinity of e to the minus rho t u prime ct times at, and that's equal to 0. So our wealth time t multiplied by our discounted marginal utility at time t, and the limit as t goes to infinity, that should equal to 0. That's perhaps a more familiar form of the transversality condition. And I hope this way of deriving the transversality condition, of solving the first order condition of the household, I hope this method has made it clear exactly what the transversality condition does and the role it plays, and made it a little more clear how it's derived. In the next video, I'm going to take this first order condition and I'm going to use it to derive our familiar Euler equation, which is going to tell us how our marginal utility of consumption, or just our consumption, evolves over time on the optimal path. So thanks very much. I'll see you in the next video.